Good morning, everyone. My name is Ansar Sheikh, Triple E Department, St. Peter's Engineering College. Today, in this lecture, I am going to tell about state space analysis. The main agenda of this lecture is that state variables of dynamical system. What is a state? What is a state vector? What are the state variables? And then state variable equation. What is meant by an state variable equation? What is an output equation? Why we are going for state space approach? The reason a transfer function approach is already exist. Then why we are going for an state space approach? That thing also we are going to discuss. And how you are going to convert the transfer function to state equation, and similarly state equation to transfer function. And last one is a time response and state transition matrix. What is a state transition matrix? How we are going to find the state transition matrix? What are the properties of state transition matrix? This is the main agenda of this lecture. Here we are going to define first what is the state, what is an state variables, what is an state equation, what is the output equation, why we are going to use an state equations, and how we are going to convert the transfer function to state space, and then what is the time response of state transition matrix, and what are the properties of state transition matrix, and problems and examples also. Introduction. Already we know that classical control theory already we studied. In classical control theory, just we are going to concentrate on transfer function analysis. What is the transfer function analysis, and why already existing transfer function analysis is there? Then why we are going to prefer modern control theory or state space analysis? In classical control theory, there are some difficulties are there. That is, it will be going to be a limit with a single input and a single output systems only. It will be useful for only linear control systems, and it will be having always initial conditions. Coming to modern control theory, it is not having it can be useful for non-linear systems or linear time variant systems, or we can use for multiple input and multiple output systems also. So that because of these 3 to 4 reasons, we are focusing on state space analysis. That is that the state space analysis advantages are that it can be used for multiple input multiple output systems, non-linear systems, linear variant systems also. So that we are preferring used to state space analysis. Now definition, how we are having in this diagram, we are having a state variables, input and output. What are the state variables? X1, x2 and so on xn, we call it as an state variables. u1, u2, u3 and so on ur, we call it as an input variables. And y, y2 and so on yp, we call it as an output variables. And first we have to know that what is meant by an state. The state of dynamic system is the smallest set of variables. What are the state variables? Set of variables is x1, x2 and so on xn. At that particular instant of time, if you want to find how is my system behavior, we can find that state variables. We can find at t to t naught. That means we can find the system behavior at any state of the at any point of the time, that we call it as an a state. Here we can give here we are having an in this particular system we are having an a multiple input and multiple output, which is involving an a n integer state variables. That's only I am representing here x1, x2 and so on xn. That is that input variables. And input I am going to go with a number of inputs u1 of t, u2 of t and so on ur of t. Whenever we are having a multiple inputs, then we are automatically we are going to get multiple outputs, that is y1 of t, y2 of t and so on yp of t. This is the state. Generally, how you are going to get a state equation and output equation, that is the basic representation, that is a general state representation. There is no confusion at all. That means how we are going to get is nothing but x dot of t is equal to ax of t plus b into u of t. That equation we call it as a state equation and or dynamic equation. Output equation y of t is equal to cx of t plus du of t. That is the general representation of state equation. From this, what is an x? Just normally we know x is an state vector. X is equal to dx of t by dt, which is equal to derivative of the state vector. That we call it as an x dot of t. X dot of t is equal to dx of t by dt. And u is nothing but an input vector. Y is an output vector. Here all constants a, b, c, d all are matrices, where a we call it as a state matrix or system matrix, b we call it as an input matrix, c we call it as an output matrix, and d we call it as an feedback matrix. A, b, c, d are the matrices, and x dot t is an input, x dot t is an derivative of state vector, x is an state vector, y is an output, and u is an input vector. Here see here I am giving an a what is the order on the order of the matrices, and that is an x dot of t is equal to ax of t plus bu of t, that we call it as a dynamic equation, and output equation y of t is equal to cx of t plus d into u of t. The state vector consisting of a number of state variables, that is a state vector is x1 of t. It consisting of an n number of state variables, that is x1 of t, x2 of t, x3 of t and so on. Similarly, input and output also. Now the what is the order of the matrix? A is n by n matrix, b is n by r matrix, c is an p by n, and d is an p by r matrices. That is the size of the matrices. As we know that a, b, c, d are an matrices. Here a is a matrix size is n by n, b is an n by r, c is an p by n, and d is an p by r matrices. Now the block diagram representation of a state model. How you are going to get the block diagram representation is x dot of t is equal to ax of t plus bu of t, and y of t is equal to cx of t plus du of t. By using that all equations, we are going to get this block diagram representation. Here see here x of t is nothing but you are the what is that input you are getting b into u of t, and a into x of t. If you are taking that output of the x of t is nothing but a into x of t plus b into u of t. And similarly, you are taking an y of t is nothing but c into x of t plus d into u of t. That is the block diagram representation of the state equations. This is the concept input-output models versus state space models. Input-output models is nothing but transfer function model versus state space model. State space model, what that means, and what are the comparison between state space analysis and transfer function analysis. All we know that just now we can find that in a state space model we can find the internal behavior of the system also. We can find the multiple output MO and non-linear systems behavior also. But input output models it will be useful for only linear and time domain specifications, and it will be used for only Laplace transformation method only. But in case of state space model, we are not using any Laplace transform method. Here in the case of transfer function, we are using a Laplace transformation. What is a system variable? Some definitions. Why? Because we are entering into a new model, new concept, that means a state space analysis. Whenever we are discussing a state space analysis, we have to know that some basic definitions. What is a system variable? What is a state variable? What is a state vector? What is meant by a state space? System variable is nothing but it is a variable that responds to an input or initial conditions in a system. Any Whenever it will be going to a respond, whatever it may be the variable, for example current, voltage, all will be going to be a variable varies whenever you are giving some input. That variables we call it as system variables. State variables is nothing but the small set of linearly independent system variables such that the values of the members of the set at time t naught along with known forcing functions completely determine the value of all system variables for all t greater than or equal to t naught. That means that we can find the system behavior at any instant of time. That means whenever we are starting from after that, at any instant of time we can find the system behavior. Next, state vector. A vector whose elements are the state variables, just we are considering in the vector form. State space, that is from the differential equations we are going to consider. Output equation, the output variables of a system can be considered as an output equation. General state representation, we are having a particular subset of all possible system variables, state variables, all will be there in a state space representation. For nth order will be there. If you know the initial condition of all state variables as t naught as well as the system input for t greater than t naught, we can solve the equation. That is that thing only. The state space analysis, either you can use at the initial state or at any other state also we can represent. Yes. For example, the state equation of an nth order system of a linear differential equation, always we consider y power n plus a power n minus 1 into y plus a n minus 1. That is an nth order differential equation in the form of y, where what is the y? Already we know that where y is the system output and u is the input of the system. If you are considering an nth order equation, then automatically we are having an n integer state variables. For that state variables we are going to represent with x1, x2 and so on xn. So I am going to consider, let us define the state variables in the form of x1 is equal to y, x2 is equal to y dot, x3 is equal to y double dot, x4 is equal to y triple dot, like that, and so on. Xn is equal to y power n minus 1. See here, states representation of the nth order. In the last slide we are considering x1 is equal to y. Then what about the x2? We can consider like this: x1 dot is equal to x2, x2 dot equal to x3, x dot n minus 1 equal to xn. Then what is the x3 dot? x3 dot equal to x4, like that we have to consider. And finally we are getting xn dot is equal to all n number of integers will become. Let's see here, this is the basic representation of the matrix. How we are going to write x is equal to, x is nothing but an state equation is equal to x dot is equal to, it consisting of an state variables x1 x2 and so on xn. The matrix in the first case, what is the a is equal to, what is the coefficient of x1, x1 equal to what we are getting, x1 dot equal to x2, x1 dot equal to x2, so that x1 dot is equal to x2 means all the remaining coefficients of except x2, remaining all coefficient will be the 0. Why? Because x1 dot is equal to x2, in the only in the place of x2 only you are getting 1. In the second equation, x2 dot is equal to x3, all the except x2 dot is equal to x3 means which coefficient will be the 1, x3 coefficient will be the 1, so that this is 0 is an x1, x2 is an 0, x3 is an 1, like that, and so on 0. That means in the fourth third row what we will get, 3 zeros and then 1. Why? Because x3 dot equal to x4, like that we are going to write down, we are going to writing. And finally what we are getting, xn dot is equal to, in the you check that these matrices with the previous slide, that is xn dot equal to what equation you are getting, minus an x1 minus a1 x1 xn and so on u of t and so on and so on u of t. What is that? Is there in the first equation x2 x1 dot is equal to x2, is there any u coefficient? No, 0. So that in the B matrix the first element is 0, and x2 dot is equal to x3, is there any u coefficient? There is no u coefficient, so that the second element is also 0, like that we are going to write. In the last equation, x dot equal to minus an minus x minus an minus 2 minus a1, the b coefficient will be also u, so that we are getting an 1. This is a simple representation of an x and a matrix and b matrix. The matrices a and b matrices will be depends upon these equations, that is an x1 dot equation and x2 dot equation, like that we are going to if depending upon these equations only we are going to get these matrices a and b. And similarly we written here only a state equation, we have to write y equation also. Y is nothing but an output equation. What is the output equation we consider in this slide? In this slide what we are going to consider, y is equal to x1, y is equal to x1, so that we have to get y is equal to x1, the state equation y is equal to, in the form what is that, y is equal to cx plus du. So you are having an c is equal to, only x1 coefficient will be there, so that I am writing 1. If it is an x2 coefficient also it is there, then again 1 you are getting, there is an no d coefficient, so that the matrix D will be equal to 0. Now you have to consider what is this diagram? We are having a mathematical representation for a mechanical system. That mechanical system will be consisting of a mass m sorry, mass m and the damper b and the stiffness constant k, and we are applying the force f of t. In this system, which system already we know that what is that, m into d square x by dt square we are getting, so that it must be a second order system, so that the matrix size must be a 2 by 2 matrix. All of you remember that thing. M is equal to d square m into d square x by dt square, force f of t is equal to, whenever you are having a mass m, f is equal to m into d square x by dt square, so that we are getting second order differential equation, so that we are getting two state variables. Let us define state variables x1 and x2. What is that? X1 equal to y is equal to x2, and what about the x2 value? X2 value is nothing but, we are considering that from this equation you need to find out what is the y value. What is the y value? Y you take it out common, then you are taking y is equal to 1 by m into 1 by m minus 1 by you are just find out the y value from this equation. That is a simple thing. After finding this, you are getting an x1 y is equal to first equation. What you are getting, x1 is equal to y, x1 is equal to y, you are getting x1 dot is equal to that means an x1 dot is equal to x2, so that you are getting an 0 and 1. X2 dot is equal to, you are getting x1 is equal to y, which is equal to x2, so that what about the x1 dot, x1 dot equal to x2, x1 dot equal to x2, that means 0 and 1 you are getting. Similarly, x2 dot is equal to how much you are getting, x2 dot is equal to these values you are going to write down, and output equation after that block diagram representation. This is for electrical system. How you are, these are the two methods here we are representing. Always you are going to write a KVL loop equation, then you are getting this equation, and similarly you are doing the same thing here also. And some few more examples here I am represented. This thing normally see here how you are going to write down. This is the transfer function I given to you, c double dot plus 9c c triple dot 9c double dot plus 26 dot plus 24c, which is equal to 24r, where c is an output and r is an input. What we are going to consider, the first equation always what we are going to consider, y is equal to x1 and y is equal to x1, then x1 dot equal to x2, see here x1 dot equal to x2 and x2 dot equal to x3. Now how you are going to write this x1 dot equal to x2, x2 dot equal to x3, and what is that x3 dot is nothing but c triple dot, c triple dot equal to how much, minus 24. is just a substitute wherever you are having an these values. X1 is equal to c, in the place of x1 you need to substitute c, x2 you need to substitute c dot, x3 you need to substitute c double dot. Wherever you are having an c double dot you need to substitute which value, x3. What is that x3 dot, x3 dot is equal to c triple dot. Wherever you are having an c triple dot you need to substitute x3. Wherever you are having an c double dot is equal to how much, x2, c double dot equal to x3, x3 dot is equal to c triple dot, x3 is equal to c double dot, x2 is equal to c double dot. These three values you need to substitute in that equation, then you are getting an x3 dot is equal to x3 dot, why I am writing x3 dot is nothing but what, c triple dot is equal to how much, minus 24r minus 24c minus 26c dot minus 9c double dot. What is in a c double dot, x3, c dot means x2, c means x1, and r means r. Now finally which equation you are getting, this equation. Similarly, what is the output equation, y is equal to c into x1. Now by using these equations you need to write down what we are going to write down, the state equations. State equation is nothing but x dot is equal to ax plus bu and y is equal to cx plus du. I am writing here. What is the value, x1 dot, x2 dot, x3 dot, that is a vertical matrix. Now what is the coefficient of the first row, x1 dot is equal to 0, x1 coefficient is 0, after that 1 and then 0. Similarly, x2 dot means which coefficient, 0 0 1, x3 dot is equal to, on the last row what you are getting, minus 24, minus 26 and minus 9. What about the B matrix, 0 0, what about last one is 24. That is the thing here we are writing, 0 0 24, 0 1 0, 0 0 1, minus 24, minus 9. And similarly output equation with that block diagram. That is an state space to transfer function to state space. Whenever we are giving a transfer function to you, in the transfer function you need to replace that all variables like this. First you need to consider x1 is equal to y. Here why we are not going to consider with an y means here he given that c, so that you need to consider c. X2 is equal to c dot, x3 is equal to c double dot, like that. Same for any problem you need to consider. Now we discussed about how you are going to convert the transfer function to state space. Similarly, the problem is that again if I am giving an state equations, that is in the form of x dot is equal to ax plus bu and y is equal to cx plus du, then how you are going to find out the transfer function analysis? For that, see, the state representation always nth order equation. After that I am writing that differential equation in S domain, and then we are finding y of s by u of s value like this, and then I am writing the equation that controllable canonical form, and this is observable. All equations we are writing, these are not required for you. State space model to transfer function. See, now I am giving an only state equations to you, that is an x dot is equal to ax plus bu and y is equal to cx plus du. Then how you are going to transfer that into a transfer function analysis? That is from this equation, first you need to apply the Laplace transform and then find the x of s value. X of s is equal to what you are getting, si minus a whole inverse into b into u of s, and from the output equation y of s, you are having in the place of x of s you need to substitute si minus a whole inverse into b into u of s. Finally you are getting c into transfer function is equal to c into si minus a whole inverse into b plus ds. Here, see, here I am giving matrices. What is the matrices I given? X is equal to x dot is equal to 0 1 0 0 1 ax plus bu. From that you need to find out first si minus a. After that si minus a whole inverse. After that you multiply that si minus whole inverse with c, and then add c into si minus whole inverse into a into b, then and then you multiply with b and then add d value. Then you are getting the transfer function like this. This is the formula. T of s is equal to c into si minus a whole inverse into b plus d. All these matrices we are getting from the given state equations, that is x dot of t equal to ax plus bu and y is equal to cx plus du. From that state equation only we are getting, and just simplification and mathematical matrices calculation, multiplication, subtraction, where I is an identity matrix which is order of a. The identity matrix will be equal to the size of the identity matrix will be equal to the order of the matrix of A. This is the same, some different problems see into. And the last one is an state transition matrix. How you are going to state transition matrix? Again, from the state transition matrix also we are going to find out from the state equations only. Already we know the state equations, and homogeneous solution and heterogeneous solution both will be there, but we are going to go with an only homogeneous solution. That homogeneous solution means we need to consider x dot of t is equal to ax of t. Once if you know that x dot is equal to ax of t, then you apply the Laplace transform, and then from that x of s we are getting an si minus a whole inverse. From that state transition matrix, after that again you need to apply an inverse Laplace transform, then you are getting an e power at equal to inverse Laplace transform of si minus a whole inverse.